Yeah, good morning, good afternoon, good evening, wherever you are. Welcome to the 75th WTA seminar today. I'm really very happy and privileged to welcome Professor Paolo Vavassori, who actually does not need any introduction, I think, to this community. But there might be some new young students who may not know him, so I will tell a few words about him. But first of all, I like to thank on behalf of my W2S team, my co-convener, Dr. Brajbhushan Singh, my other members, Puspendra, Abhishek, Shakti, Ajar, and others, and my lab and all the audience, to Professor Vavassori for kindly agreeing to give a lecture. He was already here 3 years ago in the IC Magma conference, and it was really nice to have him, and I'm really happy that Paolo agreed to give a talk. And because of people like Paolo, we are managing this webinar series, and it's going pretty well, I would say. Today is the 75th and probably the last talk of this year. And again, we will resume the next talk on January 13th by Professor Ramamurthy Ramesh from Berkeley. And then it continues like that, at least for several months. And yeah, so I also thank all the participants who have been very kind in supporting and joining, interacting, and making this program a success. Now regarding Professor Vavassori, so he is working at Nanogun in Spain. He's a full professor leading a group. His educational career, so he has received his MSc in Electronics Engineer and later the PhD in Experimental Physics at the Politecnico of Milan in Italy, where he started his scientific career studying electronic correlation in rare earth and transition metal alloys. Later, he was awarded a postdoctoral fellowship in physics to conduct an independent research project on the investigation of magnetic fields by non-invasive optical probes based on the Magneto Optics air effect, that's popularly known as MOOC. And I must say, Paolo, that when I was doing PhD, I was reading your vector MOOC and other interesting papers on MOOC, and I really learned a lot. Okay, so afterwards, he became lecturer in electromagnetism at the same university. In 1997, he was awarded his second postdoctoral fellowship in condensed matter physics to join the magnetism group of the Material Science Division at Argonne National Laboratory in Chicago. And there he had led a project aimed at the design and study of nanostructured magnetic arrays as candidates for new generation of high-density magnetic memory media. He developed a novel MOOC approach that exploits light diffracted by magnetic arrays to access nanoscale space-resolved information of their collective magnetic behavior. So then he came back to Italy in 1999 at Ferrara University as a permanent research professor in physics. He established an independent program on magnetic nanostructures and continued to work for some time. In 2008, he was awarded the European Union FB7 IEF Marie Curie Senior Research Mobility Fellowship to join the nanomagnetism group at CIC Nanogun at San Sebastian. And in 2010, he was awarded the Ikerbas Research Professorship and became the co-leader of the nanomagnetism group. At CIC Nanogun, the focus of his research broadened considerably, encompassing the study of novel magnetoplasmonic nanostructure metamaterials and unconventional applications of magnetic nanostructures to biology and medicine. Paolo has co-authored nearly more than 210 peer-reviewed international publications and has a citation nearly 5,000. And he has delivered about 100 invited talks at different conferences and institutions. He is the co-convener of 3 issued patents, and he has been research evaluators for different countries and symposium organizer for more than 20 international conferences. He was a senior member of the IEEE Magnetic Society Technical Committee between 2010 to 2015, and a visiting professor at Le Mans University and École Polytechnique from 2019. Since 2010, he is associated editor in the Journal of Applied Physics. So with this introduction, I think we now know who is Paolo Vavassori, and I'm really privileged again to welcome you, Paolo. Just a small announcement regarding the seminar. So during the lecture, we don't take any questions. If you have one, then kindly write in the chat box or just raise hand, At the end of the lecture, we will take all questions one by one. We try to take all the questions. And just right after his lecture, we will take a group photo. So I would request everyone to turn on the camera for 30 seconds and we take some screenshots, and then we will continue with the question answer session, and then finally we'll present a small memento and we will close. So this is the plan of the lecture. Now it's all over to Paolo, and please start your lecture. Thank you so much.
Thank you much to you and all the organizers that helped you to organize this incredible, nicely event. Good day to everyone. And I'm very honored actually to deliver a talk here together with other people like Albert Fert, for instance. And so what I'm going to talk about is a kind of frontier between optics and magnetism. You see the title. So when plasmons meet magnetism. So that's a broad, I wanted just to show where Nanogune is, San Sebastian is in Europe, here in Spain, and at the border with France. This is the Atlantic Ocean. You know already because I heard that Luis Hueso already gave a talk, so a seminar, so you know where we are. And this is a picture of our research center, and this is the city of San Sebastian. So I would like to focus mainly on the thermoplasmonics, so the effect of using plasmons to play with heat and with magnetism. But since the use of plasmon together with magnetism is much broader, I will try to spend 5, maximum 10 minutes to give just a flavor. So not too much details, but just a kind of show off, a showcase of what is the implication of using plasmon with magnetism. So first of all, we have to understand what is a plasmon. Actually, what is a plasmon polarity? So you know that in matter, you can have several elementary excitations like phonons, plasmons, and excitons. So plasmons are actually collective electrons, oscillations, free electrons. So it's typical of metals. So we will be talking about metals mostly. And a polariton is basically a special state or a special configuration in which light get coupled to this elementary excitation, but not just exciting them, it's really coupled. So it means that it transfers energy to the excitation gives back energy to the electromagnetic field, and so on and so forth. So you create a kind of hybrid situation in which the system is neither light nor matter, is a new state, let's say, is a polariton. So what we will be talking about is when we create such a situation using this collective electrons, oscillations, and light. This is called plasmon polarity. Okay, this is very special, and you understand in a few moments. I give an introduction just to make you to understand what is exactly the mechanism that gives this incredible situation where the two worlds are mixed together. Okay, first of all, let's consider a small metal particle. Let's say use gold. Small means nanometer size, and we send light, an electric field, so light, on the particle. So you can imagine that we create a displacement of the charges following the electric field of the light. So the light is moving, and the electric field is going up and down. So we create an electric dipole in the particle. Okay, and that dipole, since it's an oscillating electric dipole, irradiates energy, electromagnetic wave in space. Okay, this is just a coupling of light with charges. This is not a plasmon. Is not a polariton. So we need to have some mechanism that create a resonance, a strong coupling. Where this coming from? So we said the electric field creates this displacement that fluctuates with time, but we have to consider that if you look what's happening inside your particle when the charge is, so the electron is being moved down here, like is in this picture, that inside your nanostructure, you create an electric field that goes from the plus to the minus charges, which is opposite to the field that you apply outside. This is called depolarizing field. And this field has an amplitude which is proportional to the displacement. So it's proportional to the dipole itself. Okay, so you can imagine this. This should remind you about something. You have a system where you have some particles that move, but when they move, they create a recoiling force, which is proportional to the movement, to the displacement. And obviously, this is a real metal, so in the movement, you have dissipation. Should remind you about an harmonic oscillator, a damped harmonic oscillator, and that's an incredibly powerful and simple analogy, but it's working very well. And the harmonic oscillator, you might know, is a very, I don't think that's taught to the proper level in the physics course. It's something that you probably learn during the first year of your university or even in high school. But the physics is very fascinating because you know that if you have a force, oscillating force, in our case, the electric field, you have a mass, in our case, the electrons, and you have a spring with a certain rigidity. In our case, is this depolarizing field. And then you have some dissipation, a friction, which is some mechanism that we will see later. Then you can have a resonant behavior. So if you hit the right frequency, actually you create a very large oscillation of your mass, of your electrons in our case. And so you can create an oscillation that is much larger than the one you can have in a system where this recoiling force is not present. For instance, in our case, a film. If you shine light on a film, you don't have such a resonance. So this resonance is the mechanism that creates this strong coupling between light and electrons. And the one thing that is very relevant to notice is that there is a phase in the movement. So when you hit the maximum amplitude of the oscillation, actually this oscillation is happening at 90 degrees out of phase. So everybody has experienced this when you go on a swing, and if you think of what you are doing to increase the amplitude of oscillation, you ask someone to push you, or you use your legs not in phase with the movement, and that's create an increasing amplitude in the oscillations. Okay, so that's the resonance. So it means that the electric field is not just displacing the charge, but while it's doing, it's creating a recoiling force. The recoiling force is creating this motion out of phase, and this creates an interesting effect that the amplitude of the oscillation can grow much higher than the oscillation that you can have if you don't have this mechanism in place. Actually, the response in terms of amplitude in function of the frequency of the electric field as this form, and actually one can characterize the resonance behavior by what is called a quality factor, which is basically the ratio between the resonance frequency and the full width maximum of this peak, or equivalent, you can use the wavelength. And the meaning of the quality factor, it tells you how much is the ratio between the energy that you store there in your system divided by the energy that you dissipate during a cycle. If you don't have dissipation, then you can accumulate energy infinite, and then the system would explode. So we need to have some dissipation to keep the system alive. Okay, so in this situation, you can imagine that light is actually moving inside your particle more times and transfer energy over not one cycle, but over several cycles, and that creates a strong matter-light interaction. That's the polarity. Okay, so how do you see it? How do you measure that you create a polariton, a plasmon, localized surface plasmon polarity or not? Okay, you have a sample. Normally are particles, metal particles on a transparent substrate. You send white light, and you look at the light that emerges from the other side. So you put a spectrometer, you analyze as a function of frequency. And what you see that the transmitted light will have a dip, very marked dip with this typical shape. So normally one plot, one minus this transmittance. So you have this peak. So that peak tells you that you have a mechanism, you have excited the mechanism where you are able to transfer a lot of energy to your system, and this energy, why is not longer visible here? Because partially is dissipated and partially it's scattered, is diffused away. So it's energy that is light that is missing on your detector. So You will see many of these plots during the presentation. I wanted to show how you is the characteristic fingerprints in an optical measurement of the plasma. So is in the transmitted light is a dip, and then you conveniently plot 1 minus the transmitted, you have such a peak. Okay, so as we said, we have this transfer of energy to your particle, then the losses, so the energy is lost because you emit light scattering, that's energy that goes out from your system, and also you can dissipate energy internally. Okay, just to give you an idea from the width of this resonance, you can also estimate what is the lifetime of the process. So how long time it's needed to the electromagnetic field to set up the steady state. So how much energy you are transferred there. And if you can calculate easily using this formula, what is the lifetime, it turns out to be for gold, for instance, a certain wavelength on the order of 7 femtoseconds. You can consider that light here, each period has a duration of 2 femtoseconds. So it means that you're transferring light over several cycles. That's the mechanism that create this peculiar state. What is used for? Well, if you create a very strong dipole, you can create a very strong field localized around your particle. So you have a stronger sub-wavelength localization of electromagnetic energy around your nanostructure. And actually the volume in which the field is amplified, thanks to the generation of this super strong electric dipole, is in the order of 10 nanometers. So it's in the order of the size of the particle. This is used, for instance, for doing imaging, well below the diffraction limit. You know, the diffraction limit is what image you can do with light is limited to lambda divided by 2. But here, the limit is determined by the size of the particle. So you can do imaging of the surfaces using the excitation of such resonance on the tip of an AFM, for instance, with a resolution which is the size of the tip. So it can be 10 nanometers. And that's independent of the wavelength you're using. You can use in micro, you want to do Raman, use 10 micron wavelength, then you focus down at 10 nanometers. So you can do, for instance, Raman spectroscopy at the 10 nanometers resolution with a very high electric field. So you can see even single molecules. Another property is that how you tune the position of this, the frequency of the wavelengths at which this resonance is occurring by size, because the bigger you make the particles, the further apart you put these plus and minus charges that you are creating. That means that the internal field, this depolarizing field, is lower, and that is the stiffness of your spring. If you think of a harmonic oscillator, you make the spring softer, so the frequency shifted to a lower frequency, which means here a larger wavelength. So by size, you tune the position. Or you can change the environmental medium around, because if you put, instead of vacuum, you put molecules, the molecules create an electric dipole that tends to screen the charges on the surface of the metal sphere. So the charges get lower, and again, the internal field, this depolarizing field gets lower, and then again, the spring constant gets lower, and the resonance shifted to longer wavelengths, which means a shorter frequency. So by changing the embedded medium, you see a shift on the resonance. And this is used for sensing, for instance. You can detect molecules just by detecting the shift of this resonance. Then you can play with shape. You can make elongated shape. This is relevant for what I'm going to tell later. And here you have 2 plasmons, again, due to the size effect. If you put light with electric field along this long direction, the charges are created here and here. They are further apart, so the spring constant is lower. So the resonance will be towards the longer wavelengths. If you put the polarization field in this direction, the charges are created here and here. So they are closer, the depolarizing field is stronger, the spring constant is stronger, so the resonance will be on the shorter wavelengths, which means higher frequencies. And so you can actually, in one particle, have 2 different plasmons depending on the direction of the polarization of light. Then you can couple these objects together, create not just one single resonator, but resonators that are making like couples of this object or even more complicated configuration, and you create peculiar responses, optical responses due to the combination of the oscillations. So, and then it's called creating the optical metamaterials. You can also exploit the periodic arrays, combining them in several arrangements, and this is all to manipulate optics. So you can create system in which you send light, and the light is by the design of these objects can be shifted or twisted in different direction, or you can change the polarization as you will in a way that you cannot do with normal materials. So they are metamaterials in which you exploit the resonances of complex resonator with their amplitude and phase to manipulate light. Okay, that's very nice, but let's move to magnetism. How magnetism here can be useful? Well, these objects that you create, these metamaterials, are designed to do one operation, but when you make it, the operation, the functionality is fixed. Would be nice to have some way to manipulate the response with an external stimulus. So the idea is, okay, we need metals. Why don't we use ferromagnets in which we can we can modify the magnetization state? Maybe they are metals, so they support this Plasmon polarities. Maybe using the magnetization, we can do some active action on our metamaterial, but we need the mechanism to couple light and magnetism. Is there a mechanism? Well, we know that ferromagnetic material have some optical activity. So it means that if you send light polarized in one direction and you magnetize the system with an external field in different direction, you can change already the polarization of light. So in the general case, you create an elliptical polarization if you start from a linear one. And you can characterize the ellipse. So to characterize an elliptical polarization, you need two quantities. For instance, these two angles, how the long axis of the ellipse is rotated with respect to the initial polarization, which is called Kerr rotation in reflection, or Faraday rotation in transmission, and the ratio between the short and the long axis of the ellipses, which is called is this angle, which is the ellipticity. So it seems that so a magnetic material can play a role there, but the effect is very small, unfortunately. So it's, normally in metals, it's very small, it's less than 1 degree. That's why we started playing with plasmon, because now with this Plasmon Polarity, we can increase this the electrodynamics through this accumulation of energy over several periods. That makes the interaction with matter stronger. And so we hopefully can increase this effect, this magneto-optical effect, and make it useful for devices like metamaterials in which the combination of the plasmon and the magneto-optical activity can produce metamaterials to manipulate light in a more efficient way and actively. Okay, and then this has been done. We did in several, we demonstrated this work. In particular, you can use also this combination between magneto-optical properties and the excitation of plasmon to design a special polarization response. Remember that we have the phase that we can produce through the plasmon. So the phase can be used to create a modification of polarization. You create line shapes in the response, for instance, in the ellipticity that goes to 0 at some values, which is related to the position of the plasmon. So if you now want to use the plasmon shift for detecting molecules, if you look at the ellipticity, because you have a magnetic material, not a simple gold, you can detect a shift of something like this, respect that detecting a shift of the peak. Detecting a shift of something which is crossing 0 is a much more efficient way to measure even tiny shifts. So we increase the sensitivity of the biodetection, for instance, using magnetic materials, magnetic nanostructures that support plasma. So, and we demonstrated that in several ways. All right, but let's go now to the very focus of the talk. We said, if we go back to the LSTR, that we have dissipation of energy through scattering of light, but also through internal mechanisms. So this internal dissipation that goes into heat. So the easiest way to understand, since we are looking at free electrons that move, we don't have an interband transition, but mostly are intraband. So it means basically that we are these losses are due to scattering of electrons in the conduction band while they're moving by the electron field with phonons or impurities. So you develop heat, Joule heating. So the excitation of a local isolated plasmon resonance involves the generation of heat. Maybe this is an interesting opportunity for magnetism. This normally unwanted effect, these losses in terms of heat. Well, that's the production of heat by these nanostructures through the excitation of the Plasmon Polarity is a very active field of research. It's called Thermoplasmonics. And if you look at, there are reviews, very recent reviews about this very active field. And you see that it has many applications, can be used to treat cancer, nanomedicine, to study cell biology, to use the heat to enhance chemistry, is used for solar light harvesting, etc., etc. You don't see magnetism mentioned here. So it seems that magnetism wouldn't have an advantage of using this heat, which is associated to the excitation of the plasma. Well, but we know, for instance, that the heat is relevant in the capability of generating heat locally is relevant, for instance, in one application which is being developed, it's almost commercial now, which is heat-assisted magnetic recording, which is based on creating a strong heating locally to reduce the switching field of a bit of information, so that you can switch with a field produced by your writing and reading head. So initially the idea was just to use a lens to focus light, to use light in a film to create a local heating. Then we have actually in the most modern application of a heat-assisted magnetic recording, the use of plasmons, but not the heat created by the plasmon, but they use a small plasmon instead of a lens, a small a small gold particle to create a local field enhancement that is used to focus down the light instead of the lens to the sub-micron area to create a local heating. So plasmonic is used for magnetism, but not for the heating that the plasmonic is creating, just for the localization of the field. Ourselves, actually, we showed that we can use a small resonator, the form of ring, to concentrate light and circularly polarized light, and to achieve a plasmon-assisted or optical switching at the nanoscale. But again, we are not using the heating here. We are using actually the capability of focusing light, not the heating. So the heating seems to be not used. So we came up with an idea. I came up with an idea where actually the heating can be very useful. The idea is this. So there is a very intense study of magnetic nanostructure that behave like monodomains objects. So they have a magnetization which is uniform. They behave like giant spin. And if you organize them in networks in which you put them in interaction through the field that they generate outside, they are small magnets, you can create arrays or arrangement of dipolar field coupled magnet. And there, by geometry, you can induce what is called magnetic frustration. So you make this global system unable to reach a unique ground state, because you don't have a unique ground state if you play with the right geometry. So you can implement magnetic frustration through geometry using these nano elements. And so this give rise to a number of interesting phenomena that are relevant also for condensed matter physics, where this frustration is present in the atomic structure, in the crystal structure. So this can be used can be seen as models for studying frustration, very powerful models, because you can see them with a magnetic force microscope, and you can tune the frustration by changing the geometry, the distance. Okay. Another application that involves nanomagnets is based again on the dipolar interaction of both magnets, is what is called nanomagnetic logic. So you can use the interaction and maybe even the frustration, if you use arrays of this type, to perform logic operation. Again, exploiting the fact that they are single domain, so magnetic dipoles interacting with a stray field, with the field they produce. Okay. In both these two fields of research, very active, very interesting, well, you need to make the system, in order to develop all these interesting properties, doing computation or create these configurations where you see frustrations at play. You need to make them capable of moving and arrange themselves in interaction according to the interactions. This is not normally happening because these objects are quite big, can be 100, 200 nanometers long and 100 nanometers wide. So normally at room temperature, these objects are blocked by the shade. So they are domains, monodomains that are interacting, but the interaction is not strong enough to let the system rearrange the cell itself in order to create this thing, or to create or to generate logic operation. So you need to activate the fluctuation, the movement of the switching of these magnets in order for them to try to see if they can improve their energy by trying to comply with the interaction. So in all these applications, you need to heat up the system, okay? You need to provide thermal energy to make their fluctuation occurring over time. So the process is described, the thermal activation of these single magnets is described by an Arrhenius law, where you have a characteristic switching time, which is dependent by this tau zero, which is normally 10 to the minus 9 to 10 to the minus 10 seconds. It's a very fast intrinsic switching time. And then you have this exponential that tells you how temperature is activating, is changing this time, depending on the energy barrier that you have to overcome, okay? So how it works that then you heat up the system, this time can get shorter. Well, because you do two things. I present this slide in case the people don't know about what is shape anisotropy. So if you have a confined structure which is fully magnetized, so you develop north and south poles at the surface, you have to imagine, like before we did for the plasma, that you have also an internal magnetic field created by this magnetic poles distribution. So actually you have an energy due to the magnetic field that magnetization itself is creating. So magnetization gets an energy by interacting with the fields that magnetization creates. So it's a self-magnetostatic energy. Okay, you understand if you have an elongated shape and you put the poles far apart, you get a certain field here, which is less intense than if you try to magnetize the system in this way, where the poles will be closer to each other. So the field will be strong. So this means this configuration has a higher self-magnetostatic energy than this one. So the system will like to lie in this direction. So if you make an ellipse, that's create a kind of anisotropy, so a preferential direction of magnetization, which can be up or down along the long axis of your elongated particle. So this is unfavored, this is favored, and this can be considered as an anisotropy, which depends on the geometry, so the aspect ratio, this is this delta n, but depends on m to the square. So when you increase the temperature, magnetization goes down. And so by doing that, you reduce this constants here. So you reduce the numerator here. At the same time, you increase the denominator because you increase the temperature. So altogether, these two effects reduce this number. They make this number smaller and smaller, so the time gets smaller and smaller. And for instance, by playing with temperature, you get to a system, and the room temperature, these elements are blocked. So they don't, they have a magnetization which is along the long axis of this ellipse. But if you increase the temperature, you can get a temperature at which this time gets faster. So during the observation, let's say you can bring down this time to 1 milliseconds. When you observe it, you don't see the magnetization pointing in one direction, but it's continuously fluctuating. So you reach the super paramagnetic limit. So it's a giant moment, but it's fluctuating in time. And that's what you want for your system to be able to fluctuate and test all the possible interactions to perform logic operations or to create these peculiar arrangements. Okay, how this is done nowadays? Well, people use a heater, a resistive heater. So they heat up the entire device, which is not very good. It's not efficient, it's not fast. It takes seconds or even hours to get the right temperature. And if you want to make a device, for instance, where you have your nanomagnets integrated with CMOS logic or CMOS technology, you are heating up everything, so you are destroying your CMOS. So you would like to have a mechanism to heat up the system faster, where you want. So you want to have something that you can control in terms of the selectivity of the position and the time. So why don't using this heat that plasmons produce when you excite them? So that's the idea of we are working on. So using, since we are talking about nanoparticles, they are metals, they have plasmon, we can excite this oscillation, we can heat them up using light. So we don't need to touch them. We send light, and light can be focused down, can be polarized, and the heating can be as fast as picoseconds. So it's a very superior way of doing the heating. Okay, that's the total idea. So, and we start with an experiment. So we take elliptical elements, initially not organized in an interacting system. We wanted to study the fundamental to understand what are the, how we can manipulate this process. We make nano elements in order to increase the the production of heat. We want to have kind of low losses. So we need to have metals like gold or silver, because ferromagnets, they don't produce a very strong plasmonic resonance. So we made hybrid structure where the magnetic part is the part that you want to heat up, that in the future will produce the interactions inside the nanomagnetic logic or a artificial spinized system, this frustrated network. But we want to have a part that we use for heating, so a plasmonic nanoheater. So we make hybrid structure. So we make this type of structure. We use permalloy, which is an alloy of the nickel and iron, and we made elongated elements of different size and aspect ratio. Why? Because we know, you remember, that if we have an elongated element, the frequency or wavelength at which you can excite a plasmon in your nano heater, which is placed down here, depends on the orientation of the particle with respect to the electric field. So if I have an elongated particle like this, and I shine the light in this direction, and I manage to get the wavelength for the excitation of the plasmon, this will happen at a certain wavelength. If I go perpendicular to it, now the resonance will be more at lower wavelengths, and that's what you have. So by playing with polarization, we can get the excitation of the plasmon at different wavelengths, so we can decide whether or not to heat up a particle by playing with the polarization. Okay, everything is done, has to be done on glass or quartz, something transparent, so we can access the particle from behind for the experiment, as you will see, but it's not limited to transparent substrate. So we have elliptical particles, they're hybrid, they have a plasmonic part, which can be turned on at different wavelengths depending on the polarization. And this should produce a heating of our ferromagnet. So we wanted to study this experiment. We designed a system to do that. We use Magneto Optics So we measure polarization change of our system, arrays of particles, to measure the hysteresis loop, and from behind we heat up using a certain laser which is focused in different position, and we can control the polarization. So the setup is described more precisely here. So now we did this studying the local hysteresis loop using our magneto optical setup, which had a resolution of 10 microns, actually 5 microns. And from behind, we heat using infrared laser by changing the polarization and the position of the spot. So we can see the effect when we heat up the region we measure, or we can measure around it. So it's a very powerful methodology. So how we see that we are heating up the system. So, okay, this is again the system. So suppose now we are sending light polarized along the long axis at 700 or 800 nanometers wavelength. You will see that in that case, we will excite plasmons in the free samples. For the samples that we call B1, we are exactly at the maximum of the plasmon resonance. So there we transfer a lot of energy, and there will be a lot of heat developed in the structure. For the other particle, we are not, the resonance is shifted because it's smaller, it's shorter, so it's towards the lower wavelength. So the energy we transfer is less, so the heating will be a little bit less. And also for the longer particle, we are actually heating the plasmon in this position and not at its maximum. So the heating will be intermediate. So we expect a heating higher here, a little lower here, and intermediate here. So we did the experiment, but we need something to measure the heating. What we use? Well, we use the coercive field, because the coercive field is a measure of the shape anisotropy. We said that the shape anisotropy depends on the magnetization behavior as a function of temperature. So if we increase the temperature, we reduce the shape anisotropy, and the coercive field should get lower. So the reduction of it, we should observe a reduction of the coercive field when we send light with the right polarization. And this reduction should be proportional to the heat transfer. We did the experiment, and actually we saw exactly what we expect. So by heating up the sample, magnetization goes down, and so the coercive field goes down, and it goes down differently for the three samples. So in these samples, we are having the maximum energy transfer. So the change in coercivity is very large. In the other two samples, in this sample is much lower. In this one is intermediate, as expected, because we are transferring energy, a lot of energy on this system here, intermediate energy on this, and the lower energy on this one, which are exactly 1, 2, and 3. And then by measuring through modeling the change of magnetization and converting, and of shape anisotropy, converting in temperature, we can get a temperature scale. So we can understand, we can measure indirectly the temperature we have reached in our system. And you see that we reach quite high temperatures, 300 centigrades here, a bit larger than 200 here, 250 here. So it is a very efficient way to heat up the system. Okay, so it's really selective. So what happens if I go with the opposite polarization? So here, if I go with the opposite polarization, the resonance will be occurring. The excitation of the plasmon is occurring at the wavelength, which is not the wavelength of our laser that we're using for heating up. So when we go with a polarization along the short axis, we shouldn't see any heating. And here is the result. So in the continuous line, the blue and the red is the result of the experiment of the page before, where we have a polarization exactly along the long axis. So we are heating the particle, and the change in the coercive field is a measure of the temperature. So we say here we are increasing the temperature a lot. If we rotate the polarization and we send the same power, but now the polarization is along the short axis, the loops that you obtain as the coercive field of this dotted line, you see there's no change with the laser off and on between. So we are not transferring energy. So it's really relevant to select the right polarization. So that's a way to control the heating. Since all these elements are elongated, now we can heat them selectively using polarization. That's wonderful. What happens if we make the array more or less dense? We see another interesting effect. If the array is less dense than the original one, the heating is lower. So we see a change in the coercive field, which is much lower by making the array more diluted. So there is an effect also in the heating related to the filling factor. So how many particles you have on your substrate. This is something we need to investigate because that means something, okay? Okay, but we can reach the super paramagnetic regime in our case. Well, since it's enough to increase the power or to focus down more the field. And indeed, we can get from the original loop to the super paramagnetic loop. Perfect. But what happened now, if you reach to this point, which requires heating at 800 Kelvin, so very close to the Curie temperature, and this happens because the particles is very big. So basically, your blocking temperature, the one in which you start having the fluctuation, is very close to where the system is losing magnetization. And from thermaloy, this is 843 degrees. So you need to heat up at around 800. That's a very high temperature. What happened when you shut off the laser after you reach this point, the nice super paramagnetic limit, that the hysteresis loop is different from the original one. So it gets smaller. So you have changed some property in your particle. You might have created some intermixing. You might have created some change in the internal structure of thermaloy of your magnetic material. So we need to find a way to achieve the super paramagnetic limit at a lower temperature, which is also good if you want to make a system which is energy efficient. So one way is to change material. Let's use nickel instead of thermaloy. Nickel has a much lower Curie temperature. So we repeat the same structure, the two possible excitation of plasmon because of the shape, but now the material is nickel. So what happened now, if we use the same power, the same focusing, the same laser, the same polarization, but we go from thermaloy into nickel. This is the thermaloy case. Now, if we set the same power, let's say, of the laser for the thermaloy, we get a reduction of magnetization. So that means a coercive field reduction, which is a lot, but is still limited because the reduction of M is only this delta from here to here. With nickel, since the Curie temperature is much earlier, the reduction will be from here to here. So we change a lot the magnetization using the same temperature increase. And by doing that, we reduce a lot the coercive field, and we reach the super paramagnetic limit at a much lower temperature without destroying the particles. So one way is to change the material. So we need to have a material in which we can tune or reduce the Curie temperature, because due to the size of these elements, it happens that the fluctuations that you want to induce by temperature are very close to the Curie temperature. So the Curie temperature reduction is a key element if we want to make the system surviving and energy efficient. So there is a lot of research on materials where this can be done, because if you use pure material like nickel, iron, cobalt, or alloys of them, the temperature, the Curie temperature is fixed by the material profile. You cannot really play. Okay. What happens now if we start putting the interaction, because in the end we want to do nanomagnetic logic, so studying artificial spin-eyes. Well, what happens now is something disappointing, because when we have a system like this, where you have crosses that mimics interaction between several islands, and you use polarization, you see that basically the reduction of the coercive field using the same power changing polarization is smaller, but that's because the system is very diluted. But also we lose the selectivity, because if you look at the red and green light respect to the blue light line, the blue line is when the laser is off. Then the green and the red are the full power of our heater, but changing the polarization. We see that we lost, while before, by changing polarization, we were heating up or not the array, now is always heated up, almost similarly. Why this happened? Why we lost the selectivity? Well, we need to look at the process. Actually, the increase of temperature due to this thermoplasmonic effect, it comes from two effects. One is called self-heating. So it's really the creation of the plasmon inside the nano heater, and then in few picoseconds, everything gets heated up. And that's happened in picoseconds. It's a very fast process. It's only the electron phonon scattering that transfer the energy from the excited electrons to the crystal, so the heating. But since we are talking about arrays, this heat diffuses through the substrates. And so after a longer time, you have that your element is heating also the nearby element and so on. So you create what is called a collective heating, which is slower. It happens in nanoseconds or microseconds, but it tends to diffuse the energy all around it. And so you create an effect like a hot plate. So it's clear now in our using a continuous laser, actually one realized that the self-heating, the one that is fast, and that depends on the polarization, the excitation of the plasmon, is at minimal. The big effect comes from this hot plate effect, so the diffusion of heat around the particle. So since you are continuously pumping in energy using a CW laser, a continuous wave laser, you continue putting energy also in the substrate, in the diffusion, and in the end, after microseconds, you create a hot plate. Okay, so you lose the selectivity because now when you have your crosses, whatever polarization you pick, you are heating up something, and that heat, it goes all around, and then you lose the selectivity. That's not what we wanted, because we don't have elements that's only one direction. So what's the solution here? Because we would like to have this selectivity controlled by polarization. Well, if you look at the effect of the collective heating, this hot plate effect, it depends on how many elements you are heating up by your laser. So if you focus down the laser and you heat up less and less elements, you reduce this diffusion effect, this collective heating, and you acquire, you increase your selectivity. So this is what the temperature you can achieve by rotating polarization from one direction and the other one. So we get some selectivity recovered, but still we have an increase in temperature due to a diffusion that now is limited. Okay, so focusing down, which is possible with light, is a way to reduce the effect. But what is the most interesting effect? Well, we can play with time. We said that the diffusion operates over nanoseconds and microseconds, while the self-heating is a picosecond effect. So if you use picosecond pulses, you actually exploit only the self-heating. And so by the time the pulse has come and gone, you just heat up the elements that develops the plasmon, not the nearby elements. So you have a perfect selectivity. So by using picoseconds or nanoseconds pulses, you save energy, because now the energy is can be very high but it lasts very short time. So we are talking about picojoule, a very small energy. We can heat up selectivity particles based on their orientation respect to the light. So we can control the heating of sublattices, for instance. And then if you focus down, you can control selective heating of individual elements. So we gain again the control over the space and polarization by using picosecond. So now we know how to play. Okay, we learn that we want to have self-heating, not the hot plasmon, the hot plate. And then we can use this to do, for instance, logic operation. So we can make an arrangement of elements where we set some inputs at some value. Then we heat up a portion of it just to activate the interactions and the relaxation towards lower states, and you can get an output. Okay, and that's what we have been working. And actually, the nice thing here is that depending on the network that, let's look here, depending on the network that you create to do some logic operation, you can implement here frustration or not, depending on which elements you are heating up. That's very powerful. So you do it by optics, not heating up everything. You do it fast, gigahertz, so picosecond, let's say 1 nanosecond, and you can heat up one entire area or just some individual elements by playing with polarization and focusing. By doing that, without spending too much time, you can create different logic operations, because if you heat up one element at a time, your system is deterministic. So you don't make use of a frustration, because by heating one element, you go from one high energy to then only one possible lower energy. So the behavior is deterministic. You heat up, you set your input, you heat up your computational zone, and there, by selectively heating, you can create a response which is a switching or not of that part that is completely deterministic. If you heat up everything and the network is implementing frustration, so it doesn't have one only way to relax, you can create a response which is probabilistic. This is a very active field of research, doing not conventional logic, where you have a probabilistic or stochastic behavior. Normally, this is implemented in different systems. Here we are talking about making a network where by light, I can endorse the system, the properties of being deterministic, conventional Boolean gate, or it can be a probabilistic gate, and you can do non-conventional computing. Okay, and we did this. We're actually working on this with a group in Belgium. So we designed a very simple system to begin with, which is this system in which we have two inputs that you write using spin torque, for instance, or you can use a field. Then we have a control element that selects the operation of the is also reconfigurable, and then we heat up only the output, and the output in this case is purely deterministic, and we can create logic gates like an OR or an AND, which is activated by light in the nanosecond time scale, only 10 picojoule we use it, and by selecting this control element, this response can be the response of an OR or an AND. It's purely reconfigurable. With one set of elements, we have a logic gate that is very low energy consuming. And we are doing the experiments right now. We are just, we have a paper submitted for the theory, and now we're doing the experiment. I don't have yet results, but we have made the structures, and we are working on that. Okay, so that's the idea. We can do Boolean logic or probabilistic logic by designing arrays and using this fast, efficient polarization control optical heating. The next step that we are considering now, and then I finish, is well, what we can do to make the energy consumption even lower, because you have to imagine that the logic gate during made with CMOS technology consumes less than 1 picojoule. Here we are at 10 picojoules. We are very good, but not quite there. Well, there are strategies to improve the thermal generation, the heat generation of the elements by making hybrid system that I call hyperbolic material. So we are working on that. So we can increase the heat generation. The other thing that we can do, and then is to play with the material. As I said, we hear with Andreas Berger, actually, that he will give a talk next year, I guess, about this. We can create what they are called graded materials, in which we introduce some impurities, non-magnetic, in a film in a controlled gradient way. And by doing that, we control magnetic properties like Curie temperature, hysteresis, inducing temperature changes that are controlled at the temperature you want, not 400, 500 degrees, but even 100 degrees or less. And that's very relevant to combine our approach of the heating and making, instead of using permalloy, nickel, these new materials as materials for these arrays. And other things that we can do, and I close it here, that we're going to explore, is actually that by make arrangements of these elements in which they are oriented differently, we can create strong thermal gradients at the nanoscale or microscale, any scale you want, just by illuminating them. So they are very strong thermal gradient, and the scale is designed by the system. So we can study, and we plan to study, effects like related to spintronics, where we can use the thermal gradient generated at the nanoscale to study the spin-Seebeck effect, so the different spin accumulation due to the thermal gradient. Or these can be used to move, to drag spin configuration, spin texture like domain walls, or even skyrmions or spin waves, also dynamics, through thermal gradients that can be designed and modified, turned on and turned off, and reconfigured all by light. So it's a very powerful approach for the future, and there we are going to actually study it. So that's the end of the talk. So I think that we are really believing that this approach will open an enormous amount of opportunities in several studies in magnetism. So in the future reviews about thermoplasmonic, we hope to see also magnetism mentioned as a key field in which thermoplasmonic can have an impact. So these are my collaboration, and I thank you very much for the attention. I've been a bit long, but I hope it was of interest for you. Thank you very much.
Yeah, thank you so much, Paolo, for this excellent overview of many interesting light matter interactions. Really nice research. As I said, now I would request you to stop sharing the screen, and I request all of you to switch on your camera for 30 seconds, 1 minute. We take a picture, then for our archive, and then we will, yeah. So, Paolo, could you stop sharing the screen, please?
I'm sorry.
Yeah, sorry. Yeah, then you will again share it. And
thank you, sorry.
Difficult, yeah. Okay, let me go to the regular view. Yes, now I have the gallery view. So I request all of you to smile. All right, I have some more people. So please smile. Very good. Thank you. So we can now switch up your camera, and I request again Paolo to share the screen, and I take some questions. There are already 2 questions by Smriti Chawla. You would like to ask, or should I read your question?
Sir, I can ask.
Okay, please go ahead.
So, sir, as you told us about the frustrations in magnetic materials, can you say about the ways we can introduce it in externally or artificially?
So I don't know if I hear you intermittently, but you're talking about how I can manipulate magnetic domains.
Yes.
Its effect.
No, I think she's asking about the spin ice. about probably where you are adding some frustration by putting some special geometry. I think that's what Smriti you were asking, isn't it?
Yes, sir. And how is it different in the case of antiferromagnetic materials and ferromagnetic materials?
Well, artificial spin-ice are metamaterials, so it's not. How can I say? You want to have a system to study that effect in which you know the system is a single domain, is a giant spin. So having antiferromagnets is not an option. You want to have the material that make these elements ferromagnetic, okay? And then, because you want to have a stray field, that's the way in which these nanomagnets interact with each other. By playing with geometry, you can make this interaction frustrated. So there are naturally occurring materials that do this at the atomic level, okay? The interest in this, they are called spin-ice, okay? The artificial spin-ices, these metamaterials created with magnetic nanostructures, serves as a model because you can design a frustration that maybe in nature doesn't exist, because this material, the naturally occurring spin-ices are limited. They have a cubic structure mostly, and that's it. Here you can design system where the structure is not only cubic, but can be hexagonal, honeycomb, etc. So it gives you a broader view about the phenomenon of frustration. Frustration per se is a very relevant phenomenon, because frustration means that the system can have different responses to stimulus, not just one. It's not just magnetization that flips, but the states, the configuration of an assembly, since can have many ground states or equivalent, can have different responses to external stimuli. It's more closer to life. So it's closer to a living system, where a living system responds to external stimuli in a various way, and that is the secret of life. So, and what I want to say, that frustration empowers your system to have responses that are not just one but more. And then there is a lot to learn about phase transitions, because how the interactions affects phase transitions, so ordering in a very periodic, what you would call a domain, or a completely disordered state. So there is a lot of implications that are, let's say, fundamental for phase transition, entropy, because this system has a very large 0 Kelvin non-zero entropy. So the interest is mostly for fundamental issues about statistics and frustration, and but since now we have also all this field of research where people are still studying neuromorphic computing, where basically trying to emulate the brain, where the response exactly is not one for a stimulus. These are also envisioned, these networks, to do this special logics, which is called stochastic logic, that other people is trying to do using spintronic oscillators that interact. One way is to use this magnetic moment. But all these studies, I want to come back to my part. If you can activate all this potential using light, the gain is enormous in terms of energy saving, the fact that you can excite all this peculiar behavior at a time scale, which is not seconds, but it can be nanoseconds or even sub-nanoseconds. So you can study all these effects, or having all these functionalities that are relevant for this new field of logic, using a system where it is energy efficient, and it allows you a flexibility in the heating that is unimaginable using conventional ways. Not to mention the fact that you can use these thermal gradients to study phenomena like the propagation of skyrmions, of spin waves, of domain walls under the action of gradients. And also these gradients now you can create at any scale you want, from nanometer to microns. That's, I think, is very promising for the future. So, but these are artificial systems, so you cannot transfer this to the naturally occurring materials. To the naturally occurring materials, they do what they do, and that's it. So here we are talking about metamaterials and the power of metamaterials in going beyond what is naturally occurring. I don't know if I answered, but I guess.
Yes, I think we need to move on. Maybe I don't see other questions. I have a quick question, Paolo. For getting this excitation, so what kind of laser energy is like minimum needed? Or I mean, you need some high power laser, I guess. So could you tell a little bit more about that?
Can you say it again, please?
Yeah, the laser power.
Yeah. Right.
So what type of laser power is needed to excite and to make these studies?
It's not appropriate to talk about energy power, but it's the energy that you deliver. Okay, so we are using pulse laser. Okay, so we deliver an energy which is picojoules now, and the reason that we need to read 250 Kelvin for nickel. Okay, so the idea is that using the material that Andreas, for instance, is developing, where we can create magnetic material with a Curie temperature that are lower, or even anisotropy that varies with temperature in a very dramatic way in a regime closer to room temperature. Now we can, and also improving the thermoplasmonic heating by using this hyperbolic material, we are sure that we can go below the picojoule. So that's less than 10 to the -9 joule for doing one operation. That's basically the energy scale of CMOS logic. So we are approaching CMOS logic in terms of energy and speed, because we are talking about gigahertz. So that's very promising. Because this type of logic operation, for instance, have the advantage that being magnetic, they store operation and process of operation. While CMOS, if you want to store operation, you have to keep the system powered up. Here is the hysteretic behavior of the element. So I think that is very promising in that sense, because nanomagnetic logic has been around for a long time, but it's not really practicable. But the reason is also because you need to heat up, and the heating was really poor. Now we demonstrated this very incredible flexibility in the heating using this plasmonic oscillations excitation. But I think also spintronics, just for the properties of creating this fully designable thermal gradients at the nanoscale, that will also benefit a lot by this capability.
Okay. I think, I don't know, your internet or my internet, something is fluctuating. In any case, thank you so much, Paolo. If there are any quick questions, kindly raise your hand or, yeah. Well, I don't see. I think the lecture was very clear. And so
it was really a lot of stuff, and probably is not so familiar, but I tried my best. One question is, okay, this is a recorder, so they have the material. So please have a look and reflect a bit on the things I try to explain. I try to make it as clear as possible, but I understand this for many of you is new. I'm happy to respond to any question that would come by email later on. So please,
yes, that would be nice.
I think
So
we
people
do a
are
lot of work together because that's a powerful combination of optics and magnetism that we should take advantage of.
yeah. Okay, Paolo, I think there are no more questions. People are thanking you. Could you kindly stop sharing? I like to share my screen.
Sure.
Okay. I hope you will see my screen.
Ah, thank you.
Yeah, it is a small token of appreciation from our W2S team. So on behalf of the organizers and everyone, I like to present this to you. I will read it for you. W2S seminar, that is webinar series on spintonics, National Institute of Science, Education and Research, NIST Bhubaneswar, India. Next pleasure in presenting the plaque to Professor Paolo Vavassori from CIC Nanogun and Icovas, Spain. In recognition and appreciation for being a valuable speaker to give a lecture on when plasmons meet magnetism, plasmon-assistedopto-thermal excitation of nanomagnetic arrays. So on behalf of everyone, I clap for your excellent lecture. Thank you so much for your great talk. We all enjoyed. And so I think we can stop now. And before I say bye-bye, till the next one.
And I hope to see you soon in person.
Yes, I'm also looking forward. And I wish all the participants a very nice holiday season from next week, and a very, very happy new year 2022. Have a great year. Let's hope all this nightmare go away from our life next year. Yeah. And let's hope that. And we meet again in this online platform on January 13th by the seminar of Professor Ramamurthy Ramesh from UC Berkeley. I just want to announce that in 2022, we have made a homogeneous policy. All the talks will be 8 p.m. Indian time, except maybe some Japanese, Korean talks, which will be little before, but it will be more or less 8 p.m. throughout. This time, what is happening for the Americans, it's 8 p.m., European, other people 3 p.m. So there's a little confusion of time. So we try to reduce the confusion. Obviously, it is very difficult to remove all the time constraints because of the different time zones. So 8 p.m. on 13th June, that's 13th January, as planned, the next seminar by Professor Ramamurthy Ramesh. He will talk about exciting stuff about electrical fermions and so on. And until then, so I wish you all very happy holiday seasons and new year, and smooth transition to 2022, and good health and all success. Thank you so much, all of you. See
all
you
the
next
best
time.
to all of you.
Yes, and thank you so much, Paolo, for your excellent lecture.
You're a great person. Bye.
Thank you. Have a nice day. Bye-bye. Thank you so much.